I don't wanna grow up, I'm a curious kid. The world has 100 questions I can play with. So I'll open my arms and eyes and wonder every day till the day I die. No one really knows why gravity exists.
At this point, I would like to say welcome. I am Susan Tunis, and I am here in the glamorous office of BookShop West Portal, where I am literally overjoyed to be welcoming back our friends at Wonderfest and Dr. Suzie Sheehy, who is coming to us live from Australia, a full day away. Now I am going to turn things over to Tucker Hyatt, who is going to introduce Dr. Sheehy and host the rest of the event. Thank you all for joining us.
Thank you, Susan. I am indeed Tucker Hyatt, founding director of Wonderfest, the Bay Area beacon of science. It is my pleasure to introduce accelerator physicist and science communicator, Dr. Suzie Sheehy. Dr. Sheehy does research in particle physics at both the University of Oxford in England and the University of Melbourne in Australia. She is joining us from Australia this afternoon, or in her reference frame, tomorrow morning. Suzie earned her undergraduate degree with first-class honors in physics at the University of Melbourne, and then earned her physics PhD at Oxford. Much of her early research was done at the Daresbury lab outside Liverpool, and after joining Oxford Physics at the John Adams Institute for Accelerator Science, she became a Royal Society University Research Fellow. Even during her early research, and ever since, Dr. Sheehy has cared about science outreach. Now we get to enjoy the fruits of that public engagement through her first book, The Matter of Everything: How Curiosity, Physics, and Improbable Experiments Changed the World. Please welcome accelerator physicist and accelerating science communicator, Dr. Suzie Sheehy.
Thanks so much, Tucker, for that. That was such a beautiful introduction. I really appreciate it. And thank you to everyone for coming along today. It's really lovely to see you here. As Tucker said, I'm in the future at the moment. It's 8 a.m. on Monday morning here in Melbourne in Australia. And hopefully today, in about the next 45 minutes, I'm going to give you a bit of an overview, some of the stories and some of the key ideas from this book that I've just written called The Matter of Everything. And to sort of set the scene, I'd like to start by talking about some of the change that's happened in our world between 1900, which is around when my book starts, and today. So, for example, life expectancy was about 47 years in 1900. And today we can expect to live to, in the US, I looked up the number this morning, about 77 years on average. The US population has increased from 76.3 million in 1900 to 334 million today. And literacy globally, that is literacy over the age of 15 years, has increased from just 21%, that's the global average figure, to about 86%. So we've seen this century and a bit of huge change in our society. And this is actually one of the, I think, starkest plots that shows that, which is this enormous shift in sort of economic growth through that period. Now, this plot starts in 1820, but you could easily start it at 1900, and that sort of exponential shape would look the same. And so what's really changed in our lives is that new inventions have led to an increase in productivity so that goods are less scarce, right? So overall, there hasn't been sort of one piece of the pie and then someone's gotten more and someone's gotten less over this time frame. Growth has actually led to a positive sum economy. So even though there's way more people on Earth, they are living far better lives than ever before. And I always like to set this context because we live in such challenging times with such big questions facing us, technological challenges, scientific challenges, societal challenges, that it's actually important to realize just how far we've come in the last 100 years. Now, one of the things that I realized in writing this book, and I'm going to get to the physics in a little bit, I promise, is that all of us are pretty bad at predicting the future, right? And I would say that physicists are in that category as well. So here's a famous physicist from around 1900, Lord Kelvin. And here's his prediction of the technological expectation for the future. At this point in time, he thinks neither the balloon, the airplane, or the gliding machine will be a practical success. Not a great prediction of the future. I can pretty confidently say that he was wrong. So at the time, and if we ask people now, I think we would make a similarly wrong prediction. In 1900, for the World Fair or the World Exhibition in Paris, they made a series of postcards by artists to predict what the future would look like in about the year 2000. And it's way off the mark. And one interesting thing to observe is it's way off the mark because it doesn't go far enough. So they were just starting to think about flight. And so here everyone's obsessed with flight, but you'll notice a few things haven't changed. So the clothes people are wearing haven't changed in this prediction of the future. The architecture hasn't changed. I bet if you asked them about the food they were eating, they wouldn't have predicted that that would change. So we're pretty bad at predicting the future. And here's some other things from this postcard series. It's a beautiful little series, so I thought I'd include a few examples. So the top left is sort of how learning would happen and how information would be transferred and shared. Not quite predictive of the internet and the World Wide Web, but an interesting vision. They obviously predicted that our stuff would be made in a more automated sense, but no one predicted the giant mega factories, even if the robots were kind of, they were kind of on the mark with that. But all the automation that they predicted was mechanical in nature, not really electrical, and certainly not electronic, which I'll get back to in a little while. And of course, there seemed to be this obsession at this point in time in living under the sea. Now we've shifted our obsession away from the sea and perhaps toward outer space, but that was also an interesting prediction, which I have to say did not come true in the year 2000. Right. So let's turn to physics for a minute. At the same time, in around 1900, physicists thought that their story was pretty much done. So here's another famous physicist of the time saying that it seems probable that most of the grand underlying principles have been firmly established. And this one's quite interesting to me as well. The future truths of physical sciences are to be looked for in the sixth place of decimals. So they really thought that at this point in time, because they had gravity and electricity and magnetism, and everything was sort of predictable from the level of atoms upwards, they really thought that their work was pretty much done. They didn't expect all of physics as they had known it to kind of fall apart. And what I'm going to show you through the rest of this talk is how these two stories that I've just told you actually intertwine a little bit, and how the experiments that happened in physics both changed our understanding of how the world works and also changed our society and led to some of those technologies and innovations that have driven at least part of that growth in the last 120 years. And it sort of kicks off in around 1895, just after the discovery of radiation, which was the same year. And this is a lab in Germany that I went and visited called, which belonged to a German physicist called Wilhelm Röntgen. Now, at this point in time, it's important to know that things like the Nobel Prize didn't even exist yet, right? 1895. Radio didn't exist. For the women in the audience, bras didn't exist, perhaps, hooray, I mean, some form thereof, but not in their modern version. And no one knew the nature of atoms or nuclei, didn't know how the sun generated energy, only knew about those two forces I mentioned before. So today our labs look very different, obviously, and it was just beautiful to visit this lab and realize what had happened here, which was that this man, Wilhelm Röntgen, had seen a glowing screen across the side of his lab and decided to investigate. And as a result of that, he found these invisible rays, which we now know are high energy light, called X-rays. And he famously took this picture of his wife's hand, where you could see the ring and the bones of the hand, but not the flesh. And he very quickly went down the road, literally a few weeks later, presented it to the local medical society and demonstrated it to them to sort of say, hey, I found this thing, but instead of patenting it and keeping it to myself, I want it to be of good in the world. So he turned it over to the medical community and said, I'm here to help if you need, but you guys take this and run with it. And what a change this discovery made in our society. And that's because, in my view, one of the ideas that sort of comes out of the book is that discovery, and in particular curiosity-driven discovery, sort of makes new imaginings possible, is how I would put it. It can lead to new creative and innovative ventures. So, for example, this is an early photograph of an iguana using X-rays. You might think would have taken a lot of time before beautiful photographs like this were taken. But this was taken just about 2 weeks after the initial discovery, because the cathode ray tube that Röntgen was using in his lab, that he used to generate X-rays, there were hundreds of them in labs all over the world. And it wasn't until he made his observation and his discovery that other people could pick these up and start to use them. So doctors, of course, especially started to pick up X-rays and use them. So within a year, they were being used even remotely out on battlefields. And one of the other key things that came from this is this idea that this curiosity-driven research that I write about and I think about a lot, the usefulness of it tends to compound over time. So if you think about X-rays, for example, we now use them in medical imaging, security baggage scanners, inspecting goods, making sure that things on the production line meet their standards so that our goods are safer and more easily available to us. And some of the inventions that happen from this type of research take a long time to develop. So this is the first brain scanner or CT scanner, which you might have heard of if you've been into hospital lately. I just had one the other week to scan my whole spine to try and figure out why I had back pain. I won't go into the details of brain scans because, for some of you, it might be lunchtime, but they were pretty horrific procedures. The stories in the book before the invention of this. And some of this growth in usefulness of this kind of research only comes when different ideas coalesce over time, right? So the CT scanner was brought about by the coalescing of X-rays and detector technologies, but also the invention of computers and other things like the mathematical techniques to be able to solve the sort of scanning tomography problem that was required. Now, this obviously revolutionized medicine. But what's particularly interesting to me is that this same device, this cathode ray tube that I was talking about, was also used just a year later to discover the electron. This is by J.J. Thompson, working in Cambridge in England at the time. And one of the key ideas with these experiments is that the experimenter themselves has to always figure out how to ask good questions about nature and work on building the apparatus to actually investigate those questions. So J.J. Thompson thought, okay, well, there's obviously X-rays coming out of this tube, but there's a glowing light within the tube, and no one could answer the question of what the nature of those rays, the cathode rays, actually was. And Röntgen and his German colleagues sort of held one idea, which was that it was a form of light. But Thompson had the idea that it might be a type of particle. And so he conducted a series of experiments where he could demonstrate beyond a doubt that this was a very tiny particle, 2,000 times lighter than the lightest atom that had been discovered, which we now call the electron. And this was a pretty big revolution in science, because the idea of atoms had been held as the smallest thing in nature since the time of the ancient Greeks. So this starts to completely overthrow this idea that physics is done. And yet people still mentally struggled with it, which is one of the things I found quite interesting. So J.J. Thompson, in his memoirs, said that at first very few people believed in the existence of things smaller than atoms, and that he was told long afterwards by a distinguished physicist that had been present that he thought he was pulling their leg. He thought he was making it up. And this is one of the beautiful things that I found about digging into the stories and the memoirs and the original scientific papers of these scientists, is you get this view that instead of looking back on the history, to sort of look forward through it instead. It's a much more interesting adventure, and it shows just how much some of these scientists struggled with some of the ideas that they were coming up with. Now, Thomson's idea, within a couple of years of discovering that, he was able to explain how electrons jumped out of filaments called the thermionic emission. And this was just the thing that engineers were looking for, to be able to build devices which could switch on and off, which could transmit, which could receive, and which could amplify. And so we next get the invention of valves. They look just like the cathode ray tube, but put in sort of more of a light bulb shape. And this completely revolutionized our world. This was the birth of the electronics industry. And just quickly, the difference between electrical and electronic devices: electrical devices, the electrons flow through wires, whereas electronic devices, they travel through vacuum or through a gas, and they're much, much faster. And they have this ability to respond to electromagnetic waves or to transmit electromagnetic waves. And this really gave us such a huge boost on that curve that I showed you at the start, because then we get telecommunications, we get radio, we get the first computers. The picture on the right is the ENIAC, which used, in my notes here, it says 17,468 of these vacuum tubes. And we get even rock and roll, because without the amplifiers based on these valves, you wouldn't have that beautiful amplified sound of music. So that's what I mean by the usefulness of this kind of research compounds over time. Okay, so one of the next big ideas that came out of writing this book was, it was actually a question, which is, who gets to ask these sorts of fundamental questions, and what culture do they work in? And I'm not going to lie, digging into the history of my field, and even when I learnt it, it was very obvious to me that there was a sort of great white man narrative of the history of physics. And so one of the wonderful things that I found in researching this book was that there were women and people of colour doing this research throughout the history. You just have to look for them. And this is one of the first pictures that taught me that. This is Ernest Rutherford's research group in Montreal in 1899. And Ernest Rutherford was this bolshy New Zealander physicist, tall guy, very loud voice, used to break his students' apparatus, he used to speak so loudly. But he was generally, a friendly, encouraging person. And when he moved to Montreal, his first graduate student or master's student was this woman in the middle who you can't miss, right? She just jumps right out of the picture. And her name is Harriet Brooks. And she worked together with Rutherford and a chemist called Soddy to understand and do experiments on the nature of radiation. And in particular, she was studying this idea that something was emanating in a gas and then transforming from one type of atom to another. And her experiments, together with their other work, led to the idea that radioactive substances are actually sort of transmuting, almost like alchemists had been trying to do for many, many centuries. So this idea that a substance, an atom, which they'd always thought was stable over time, could change into another type in a certain amount of time, defined by the half-life, which is what Soddy and Rutherford end up describing. So this was a huge breakthrough. Now, Brooks's story is a little bit of a sad one. Eventually, she does go on in research. She has to turn down an engagement so that she doesn't have to quit her job when she's still a student, because that was the standard at the time in Canada until I think the late 1960s. You had to quit your job as a woman if you got married. So she throws that off. She's quite the feminist at this point in time. But eventually, when she reaches about the age of 30 and she's working over in, I think she was working in Paris at the time with Marie Curie, and she gets another proposal. And eventually at that point, she decides, well, I can't support myself very well because her family had 7 children. And so she'd always survived from scholarships and fellowships. And so she decided she would accept the marriage proposal and move back to Canada. And unfortunately for physics, that's where her contributions end. But hers was a wonderful story for me to find, was this idea that that women have always been there doing physics, even though their contributions have been overlooked or not written in the history or pushed out. All right, so let's keep moving on. So the idea of radiation and the way in which we use radiation was obviously a choice at the time. And some of the more commercial aspects were not exactly positive. So here's some examples of the ways in which radiation, or radium especially at the time, was used that might shock you today. That it was put in boot polish, it was put in butter, it was put in water, in beauty products, even in whatever that thing is. I don't know what that's for. So this just brings me to a sort of small point I want to add, which is that how we use knowledge and how we use technology is a choice that we make, right? We get to make a choice about the applications that we use, whether we're just trying to make a fast buck from it, despite the fact it might not have great health consequences, or how we can use it to actually do good in our world. Okay, so one of the other things I really discovered is that physics at this time, especially in the early 1900s through to about 1950, was a really adventurous enterprise. And now I still think is adventurous, but we sort of spend time in underground labs. But at this point in time, you really, to make discoveries, sometimes you had to go to really extreme lengths. And so in about 1910, there was this mystery of a whole lot of extra radiation that people were finding in the detectors. And the original discovery of radiation had happened from minerals in the earth. But here was this idea that, okay, if there's extra radiation that's coming from minerals in the earth, if we travel away from the earth, the amount of radiation observed should decrease. Or if we travel into the earth, which some people did by going sort of into train tunnels, underground, into water, down, under the water, the amount of radiation should increase. And that was not what they observed. And this guy, Victor Hess, eventually got a new instrument called a Wolf electroscope. He strapped it to a hot air balloon, and he did about 6 flights, up to about 5,000 feet, wrapped only in this woolen coat that he's wearing in this picture, which is must have been quite a challenge to actually take the measurements. And what he observed is that the radiation first decreased as he moved away from the Earth, but then it increased and increased further, the further he went up in the atmosphere. And what he concluded is that there's a form of radiation raining down on us from space all the time, which we now call cosmic rays. And this was, for physics, such a wonderful, groundbreaking discovery, because what this means is that there's high energy particles raining down on our atmosphere from space, interacting in the atmosphere and producing all these different secondary particles, like in the diagram on the left there. We tend to give all these different particles, some kind of symbol or names. There's pions, there's the ends are just meant to be heavy atoms. There's all sorts of things there. Now, one of the difficult things with studying radiation at the time, though, was that it's invisible, right? It's very hard to detect. And so this comes to another point of working in cultures that really cultivate curiosity. And the Cavendish lab in Cambridge in England at the time was certainly one of those places. We met J.J. Thompson earlier, who was working there. But someone else working there called Charles Wilson, or C.T.R. Wilson, was actually interested in meteorology. And he invented this chamber on the right called a cloud chamber. And at first, he wanted to study the effect of light on clouds. He wanted to study meteorology. But what he discovered was that he sort of accidentally invented the first type of particle detector, which let us visualize radiation for the first time. So I'm going to show you a little demonstration of one of these in one moment, that I set up in my office the other day and filmed. So here's an example of a cloud chamber. And what you can see here, I have not put a radiation source near this, right? These little tiny tracks that I hope you can see that appear in this chamber are one of two things. It's either the decays from radiation in the Earth, which happens occasionally, or it's these high energy cosmic rays from space that travel through us. I'm just going to play that again because it's quite mesmerizing. That travel through us all the time, and we would never have known that they were there until Wilson invented this device, or a version of this device, that enabled us to see it for the first time. And so with this new invention, a new instrument, a new experiment, we get the discovery of heaps of new different types of particles. Now, one of the things I want to point out is that at this point in time, to do a good experiment isn't just to order one, off the internet because it didn't exist, but you actually have to have a whole lot of artisan skills as well. So today, I have to know all sorts about precision engineering, but back then you would have had to be an expert in glassblowing, which Charles Wilson was. And when I was researching him, people kept referring to the sound of him blowing glass, and I didn't know what that sound was. So I went and visited our resident scientific glassblower in Melbourne, who is a rarity nowadays, and unfortunately, even since writing the book, he's actually retired already. His name is Les, and he showed me roughly how you would blow glass just to make a cylinder. It's quite a beautiful thing to watch if you've never seen it. So I'll just give it a minute. You probably can't hear the sound from this video, but the sound that they were talking about was this sort of whoosh sound of the gases burning. And then Les reassured me as well, the other sound of glass blowing is the sound of breaking glass, because it happens way more often than you might expect. So he's just heating a cylinder here, and he's got a pipe in the side of his mouth that he's slowly blowing air in just at the right time. And he's waiting for the glass, to liquefy a bit. There you go. And if we just give it a second, he's going to blow a little further. He's trying to create a bulb in the center of the glass. There we go. It's like it appears out of nowhere. It's to me, it was like black magic, him being able to blow glass and create things out of it. It's he has such a feel for it. It's really, I mean, there's obviously a lot of science behind glass blowing, but really this is an art form, right? And that's a similar thing that I see even now, is this idea that creating precision scientific apparatus and designing it is really, really a bit of an art form. So what came of all of this? What happened, in our society from all of this? Well, some of the particles that were discovered were completely unexpected. And one type of those was called muons. They're like a heavy version of an electron. And it was not obvious at all that they should have an application at all in our society. But since then, they've actually used muons because they travel through large objects, through dense rock, through things like that, without getting lost. So that means you could actually use them like a sort of giant X-ray scanner. And so today people set up these detectors to use muons coming from cosmic rays in space, like a giant X-ray scanner, to look inside things like pyramids and volcanoes, which I think is pretty cool. So they managed to find a big void in Khufu's Great Pyramid in Egypt. And today as well, they can also see the flow of magma inside volcanoes, even with a time function before it actually erupts. So this to me was an absolutely incredible thing that I learned from writing this book, which is that these fundamental particles, which have helped us understand the world, actually have uses you just would never have imagined, and that would not be possible with any other method. So just to add a few more stories of particularly the women who I found in this story, there was a competing detector to the cloud chamber at the time based on photographic plates or photographic emulsions. And that technique was invented by a woman named Marietta Blau, who had this unique background in photography and physics. And both she and Biba Chowdhury, who was an Indian researcher working with them at the time, both made amazing discoveries using these photographic plates. In particular, Biba Chowdhury discovered two new types of particles, the muon and another type called the pion, which she couldn't name at the time, but she could differentiate in her measurements between two new types of particles. And that discovery won the Nobel Prize, but not to her, to Cecil Powell, who was working in England at the time, who did a very similar measurement a few years later, but he had better quality equipment. And so his was the definitive result that won the Nobel Prize. And I know I'm mentioning a lot of these stories of women, and it was important to me to include them in the story because these few incidences are not isolated. It's really a thing which has happened over time and has been identified even back in the 1800s, which is that women's contributions are often overlooked or neglected. And the suffragist Matilda Gage was sort of the first person to notice this. And a few years ago, a science historian named Margaret Rossiter decided we need to give this effect a name. And the name of this effect is the Matilda Effect, named after Matilda Gage. So the idea of naming the Matilda Effect is to say, this is a thing that happens, and we need to work harder to include the stories of women who've made incredible contributions. And so that's exactly what I've tried to do in this book. Okay, bringing it back to the science just for a minute. So in just over 20 years, in this early part of the 20th century, we have the idea that the atom isn't the smallest object in nature, that some atoms aren't stable over time, so change is inherent. The atom is mostly empty space. Didn't get to that one, but the story's in there. That light also acts like both a particle and a wave, And in fact, all of matter does too. And that we're living in this violent shower of high energy particles coming from space. And so what starts to emerge is physics is not done, right? In fact, the universe is far richer and more complex than anyone could have ever predicted. And from here on out, it only gets more complicated. And to study that, Ernest Rutherford, who I introduced you to earlier, who by this point was the president of the Royal Society in London, he sort of made a shout out, sort of saying, I've long wanted the ability to study these things instead of just using natural radiation from radioactive bodies. He wants a source of atoms or electrons with which to study these sort of subatomic particles and to get inside the atom, and to get inside the nucleus even, which he discovered a few years earlier. And what we get then is the invention of these wonderful machines, which I now work on, called particle accelerators. So in 1932 in Rutherford's lab, we get this beautiful looking machine. Can you see the man sitting underneath the accelerator on the left there? That was how they actually made measurements on the first accelerator that split the atom. There was a little glowing screen underneath the accelerator, and the beam would come down from the top, down into this box below and hit a target. And that was how they found the first evidence that the atom had been split. Now, at the same time, there were lots of competing technologies. So on the right there is Ernest Lawrence working in the US, and he invents a type of particle accelerator that recirculates the particles and gets them up to higher and higher energy, which is called the cyclotron. And he also starts collaborating with his brother, John, who was a medical doctor. And together they actually founded the field of nuclear medicine, which was quite a remarkable interdisciplinary collaboration. And then, unfortunately, comes along World War II. Now, World War II has been labelled many times the physicist war, which is completely true. Now, my story here doesn't go into all the ins and outs of the Manhattan Project, or even the radar project that happened during World War II. But what I do want to focus on is the societal shift and the cultural shift among physicists that happened after World War II. And I think Winston Churchill actually sort of almost pushed this in his speech post-World War II, talking about the US and the fact that they created this enormous weapon, but now they had this massive military industrial complex, which was to let them act up to the level of their responsibilities, not for themselves, but for others, and then a brighter day may dawn upon human history. And a lot of physicists felt this very keenly because they had been the ones who were called in to work on the Manhattan Project. They were the ones who were successful in creating this enormous weapon of destruction. But afterwards, there were some positive takeaways that came from that. One of which is that physicists had really learned how to collaborate, how to form a massive organization, organize themselves, even if they didn't like doing that in a sort of military industrial way. And they also learned that by bringing together all these different people, that could lead to discovery and innovation that they hadn't seen before. And so in the US in particular, they built a number of massive particle accelerator labs. They kept the ones open from World War II, and they even started building new ones to let scientists around the country collaborate. And instead of focusing on sort of defense applications, to now focus more on fundamental questions and on curiosity-driven research. And this is one of those early machines. It's called the Cosmotron. It's an absolutely beautiful mid-century machine. And there's a series of these giant machines that get built that start to uncover not more simplicity in the nature of these particles, but they start to discover more and more and more new particles, and it gets really confusing until eventually there's about 200 different types of particles. But along the way, as these larger and larger machines get built, all the smaller ones start to be used for other things, and people start to realize that these technologies that have been invented for particle physics have all these spin-off applications in the rest of the world, one of which I now work on, which is the application of these tools in medicine. In fact, you might not know, but about half of all cancer treatment cases in countries where the technology is available are treated using a small particle accelerator that accelerates electrons, turns them into X-rays, and then uses that to direct radiation where it's needed to kill tumor cells, which is what we call radiotherapy. So another medical another medical breakthrough from this kind of research. Okay, so by the 1960s, we have this list of things that we've discovered. The atom has a nucleus. These big science labs bring new opportunities. We now learn that we can create radioactive substances. We can create radioisotopes, which have many uses. And also that these machines can create lots of new particles, including those so-called strange particles. So then the journey really becomes to understand the forces holding the nucleus together. Questions like, is there more than one nuclear force? How does that actually work? And in Europe, things looked a little different because post-World War II, a lot of European nations had very little financial wealth left and were pretty decimated. And so the scientists there realized that they had to join together in order to compete even with the US or perhaps with Russia on this level of curiosity-driven research. And they founded this organization called CERN in 1954, which is the European Laboratory for Particle Physics. Many of you have probably heard of it because it's now home to the Large Hadron Collider. But there's something in this science for peace, which I think really is a beautiful message to take away. So the original convention was ratified by 12 different countries, some of whom had been at war just a few years earlier. And the scientists realized that not only could they make more progress on fundamental questions this way, but they could also use this as an example of working together across borders towards something greater. And perhaps this was a peace-building project as well as a discovery project. So I'll come back to CERN in a little while. In the US, these big questions eventually led to the creation of what was at first called the National Accelerator Laboratory and is now known as Fermilab, which is just outside of Chicago. And there's a beautiful story that happens here about why it is that we do this kind of research. I'm just going to try and find the quote for a second. I've got a copy here. The director, Robert Rathbun Wilson, was standing in front of Congress. He had to justify the cost of these enormous machines to try and understand the nuclear forces inside the atom. And the senator that he was talking to sort of asked him to justify it and sort of says, you know, I understand it's a technical thing. I understand it's sort of an educational process. And at first, Wilson says, yeah, but it's also a cultural one. But this sort of goes past the senator. And he eventually asks him to justify it based on its contribution to national security. And just give me one moment because I'm going to find the quote here. There we go. So he asked Wilson whether the machine has anything to do with security of the country, and Wilson says no. He'd been involved in the Manhattan Project. He's a strong pacifist at this point in time. He wouldn't even have barbed wire fences on the site, for the record. And then the senator presses him and says nothing at all. And Wilson knocks it out of the park. He says, it has only to do with the respect with which we regard one another, the dignity of man, our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things we really venerate in this country and are patriotic about. It has nothing to do directly with defending our country, except to make it worth defending, which I think is just a beautiful quote, and the reason why we do this kind of research, even though it requires such immense facilities. Fundamentally, it's not just because of technological spin-offs, even though I'm highlighting a lot of them. Fundamentally, it's because we are curious and we want to understand the world about us. So with that being said, Wilson was also correct that there are also going to be technological spin-offs that are perhaps unpredicted. And on the left here is Helen Edwards, who was actually, they call her the architect of this machine, the Tevatron. She was an accelerator physicist who was an absolute powerhouse at Fermilab. And they built the first superconducting machine. And to do this involved buying the whole world's supply of superconducting material at that time, and taking enormous risks. And those risks massively paid off. And one of the world's largest suppliers of superconducting products today, called Teledyne, actually credit Fermilab with this, with the way in which we now build superconducting materials. So he says every program in superconductivity owes itself in some measure to the fact that Fermilab built this machine and it worked. And so today we use superconducting magnets in particular in MRI scanners. They're being used in the confinement fusion projects, and superconductors are also used in very high-speed trains as well. All right. So this brings me to another point about groups working together. And this was something that I only learned after writing the book, because we've gone through this journey now from the early days of science, where it was small labs, individual scientists, through to now the Tevatron, which was the first one with hundreds of people in collaborations. And today, of course, we're working in collaborations that have thousands of people involved. And we're working on some really hard problems. It's no longer so easy to walk into the lab and find a result which is going to overthrow physics. And I found it interesting that there have actually been studies done on difficult problem solving and group dynamics. And this was something that I've learned that I want to share with you. So MIT scientists ran a study where they put people in groups and got them to solve difficult problems. Now, this isn't a particle physics collaboration, but let's call it a simulation of one. And what was interesting is that the factors to group success were not average IQ, and they weren't the peak IQ in the group. And I'm wondering if anyone is like sort of guessing, well, what were they? The first one was a high degree of emotional intelligence or social sensitivity and responsiveness to others in the group. The second one was that groups that successfully solved the problems gave more equal time to all the members of the group. And the third one is that there were more women in the group. Now, this one correlates in our societies usually with number one, right? What's interesting is that it wasn't that it was more women in the group up to 50%. It was more women in the group overall, which is an interesting finding of this study. But I think if you just take 1 and 2 as the key features, because 3 at this point in time is correlated, I find it really interesting that it was more EQ actually than overall IQ that led to problem solving skills. And if you think about the way in which even I would say physics works, I don't think we're quite leaning into this idea yet. I think we've got a long way to go, even past learning to collaborate in the way that we currently do, to actually really lean into the best ideas that we have about how groups work together and how good collaborations work. But despite that, we have come a very, very long way. And obviously I don't have time in 45 minutes to tell you all about the many particles that have been discovered. Please feel free to read the book to learn those. But today, obviously, we have these collaborations. The Large Hadron Collider involves in some way 110 different countries and about 25,000 different people. And it is absolutely one of the pinnacles of human creativity and ingenuity. And as a result, in 2012, people discovered the Higgs boson, which was the final missing piece of the puzzle of what we now call the standard model of particle physics. But I want to remind you that none of this is about just the theory. And the reason that I chose to highlight experiments and experimental physicists in my book is because we would have no idea that this is actually how nature works unless we'd actually gone out there and done experiments. And one of the wonderful things that's happened along the way is that we've also invented things which have changed the world. So some of you might not recognize this guy. His name is Tim Berners-Lee. He was a British scientist working at CERN, and in 1989, he invented the protocols like HTTP and HTML that we now call the World Wide Web, that added to the hardware side really and put out there in the public domain for free, which is what he decided to do, created the infrastructure which we now call the World Wide Web. And imagine how different our lives would be today. We would not be able to do this today if it weren't for his invention, actually. I think one of the biggest takeaways for me in this whole 120-year story has been that even though sometimes these difficult problems seem impossible, I think what I've learned really, and what many of the physicists that I interviewed reflected back to me, is that what society can learn from this is that we can do things that seem to be impossible if we work together, and that the power that we have to collaborate is really our superpower. So I hope that going forward, even though we face many, many problems and 9 in 10 people don't think the world is actually getting better, if you reflect back to that initial graph that I showed you, also this was from 2015, this was like pre-Trump, pre-COVID, but I think what this story tells us is that by working together, we can, and by crossing boundaries between people, companies, disciplines, and countries, we can work towards solving these problems and hopefully create a better world moving forward. Which leaves me just to highlight some of the 3 key ideas of how we can do that. And that is some of the things I've picked up on already. So the first one is ask good questions. My second one would be to cultivate a culture of curiosity. That's a lot of alliteration in one phrase, but a culture of curiosity is the key thing. And also just create environments where people have the freedom to persist with these hard problems. And I'll leave it there just with a little photograph of my new research group at the University of Melbourne. And I'm very open to your questions. I can see there's some things happening in the chat already. Thank you all for your wonderful attention.
Thank you, Suzie. What a fabulous presentation. The conversation in the chat is not of the questioning nature, but is rather the thorough enjoyment nature of
oh, that's lovely.
Some private messages that are a tribute to your exquisite science communication skills. Maybe as we wait for more perhaps questions typed in the chat, or even again those who want to raise their hand and ask their questions themselves by making them visible and audible, I get to ask a question. Early in your book, you describe how there was a transition in your young life when perhaps you'd had a fascination with the world of the very tiny, as you do right now, but it was inspired really by your experience with the very large, with the vast. I'm speaking of your reference in your book to Astro Camp. Can you tell us about that?
Yeah, sure. So that was, I think a lot of people have this moment where they realize that was the moment when something clicked and they wanted to be a physicist. So a lot of my colleagues speak about similar moments. And mine, happened here in Australia, where I am back now after 15 years in the UK. And I was actually studying engineering at the time. I was studying civil engineering. I thought I was going to become a structural engineer, but I was studying physics on the side, sort of for interest. And went out with a bunch of students out to this dark sky site 2 hours outside of Melbourne. And the wonderful thing in the Southern Hemisphere and from Australia is that we face inward to our galaxy, the Milky Way, whereas in the Northern Hemisphere, because of the tilt of the Earth, you're looking outwards. What that means looking inwards is that there's this gorgeous bright band of stars across the middle of our sky here in the Southern Hemisphere. It's actually so bright that you can see the dust patches, and a lot of Indigenous and Aboriginal astronomies actually focus on constellations made of the dark patches because the brightness is so bright. So we went out there, we unpacked our telescopes, and we decided to just let our eyes adjust and lie there and just watch the night sky. And I just had this moment, which I'm sure if you've been observing the night sky, you might have had also, where you have this shift in perspective away from, your daily life and existence feeling like it's this big thing that matters. And instead I had this real felt sense of the idea that I was just a small human on the side of this giant planet, and it wasn't really the sky moving across and changing over time, which I could see. It was the movement of the planet and the solar system and the galaxy, and everything was moving with respect to one another in this enormous physical system called the universe. And I just sort of thought, the small things that I can study and learn about and do based on, gravity in structural engineering here on Earth just suddenly seemed so small compared to everything that I could learn about the universe out there. And, someone to my right, I remember, was talking about his research on black holes, and somebody else was setting up to look at planets. And I just really wanted to learn how it all fits together and how the smallest pieces connect to those largest scales in our universe. And I think that was really the moment where I was like, I didn't know I was going to become a researcher still, but I was like, okay, I have to keep studying physics. I have to figure out how I can fit this in my course. And from there, it really, one thing led to another. And eventually I decided, I was more interested in the questions that hadn't been answered. and in developing new questions about the world than I was in just applying the answers that we already had. And in this story, I also mentioned a little bit about some of my current research. So you can see here, my group is called the Medical Accelerator Physics Group. So I now work in areas which cross really between these curiosity-driven, big collider experiments and the more day-to-day application in medicine. And I love that place to be. It's like a really nice cusp to sit on in my research, to kind of take ideas and new inventions from these really cutting edge experiments and then apply them back here on Earth to try and, I guess, do some good in the world. It's been a lovely journey.
Great. Yes. Thank you for that journey. I see a hand raised. We have Kramer Winslow. Perhaps she will make herself visible and audible, and she can ask away.
Hi there. Thank you, Susie, for that wonderful talk. Oh my gosh, I came to this thinking I may not understand a thing, but there were threads that were so relevant and for what I've been looking at these days. So, oh my gosh, thank you so much for what you've done here. And I went ahead and posted my question in the chat because I wrote it down at the beginning of your talk about, I love this concept of curiosity-based research. And I can tell you do too, and that it seems like it's kind of a real ground for you. It's a very important part of what you do. And I think you answered it later, but I wanted to be sure that I did understand. I think you later, my question was going to be, what's the difference between curiosity-based and not curiosity-based? And I think it sounds like it's more motivational research because you're going to get paid to develop a destructive weapon or something. Or something.
Hopefully not, but yeah.
Anyway, if you could say any more about that, I would.
Yeah. I think I would normally define it as sort of research that doesn't necessarily have a set practical goal in mind when you set out. And I think one of the things with my sort of ask good questions and be curious is one of the key things there is, being able to conduct research with the idea in mind that you might be wrong. And for me, that's a sort of an important bit of the curiosity-driven research, as opposed to sort of applied research or even mission-driven projects or research, which is that, in a curiosity-driven sense, you might discover something completely unexpected. And I think that's where I'm trying to point to has this sort of value that can compound over time, because in other types of research, we might either sideline, ignore, or even miss those things because we're so focused on, okay, this is the path I need to take, or this is the outcome that I'm looking for, or the specific outcome I'm looking for. So it's, I guess in my mind, it's just a little bit of a different way to approach research that is really scary to some people. It sort of has a vulnerability aspect to it, because it might go nowhere, or it might, most of the time, I think a lot of people's research in this space goes nowhere. And no one wants to feel like they've spent their entire life's work researching something that turned out to be wrong. But unless they do, then we don't find the things that actually turn out to really describe the world and make progress. And I think it's a beautiful thing that so many people do spend all day, every day, delving into these questions and following their curiosity and uncovering new things about the world. And the big picture here is that our lives would be so different if those people had not done that we need to figure out really how to support those people, how to create environments in which those people thrive and are funded sufficiently, and all of those things. Yeah.
I think I'd reframe research that goes nowhere to it does go somewhere, because it tells us it doesn't work.
even finding out you're wrong is valuable, right?
Yeah, for sure. And I think there's a movement in science to publish more things that are
certainly to publish negative results. Yeah,
that's great.
Yeah,
important. It is
I'm all for that.
Okay, thank you thanks for that.
Thanks so much for the question.
Yeah, thank you, Kramer. Suzie, maybe I can ask a a question, but this might be the last one, unless there's a hand that comes up or a printed question. That's regarding your use of the term atom smasher. I hadn't heard that term, splitting the atom, in a long time. It was good to hear it again.
All right.
Yeah, the word atom, I understand, means uncuttable, right? A tome is Latin for to cut, and atome can't be cut, but a microtome does a good job of trying to cut small things. Is it odd that, and this is not an original question with me, but is it odd that we've turned to cutting atoms by ramming them together at very high speed? It's almost as if, to learn how a piano works, we push a piano down a long flight of stairs. And I take it, is it the case that there's just no other way that we can figure out to get inside?
Yeah, so I mean, one of the things I didn't get a chance to delve into is that nowadays, I think we have this idea of smashing atoms as, almost like a macroscopic idea, as you say, of smashing pianos into something and seeing all the cogs and springs fly out. Whereas the reality is, to actually get into the heart of, say, a nucleus or a charged particle even, you have to overcome the energy barrier to doing that. So that's one of the reasons why we have to put these projectiles in at very high energy. But what happens then is much more quantum mechanical in nature, right? So there's interaction probabilities, there's decay probabilities, there's this idea that you say at the Large Hadron Collider, you're smashing two protons together, and those two protons are full of quarks and gluons, and then all of that energy sort of goes in. If you have two quarks, for example, which go really near each other in that collision, basically what you're doing is taking that energy and you're turning it into something entirely new. So it's not just taking the pieces out that were inside originally, it's actually using the energy in such a concentrated way that we can generate new particles that were never there before. And it's really those interactions between the incoming and outgoing that tell us about the different ways that the forces work and the different ways in which these particles are connected. So it's kind of like, one of my friends has an analogy where he says it's like taking two apples and smashing them and getting out 3 bananas and a mango. It's not just pieces of apple, right? So yeah, which is a completely different concept, isn't it? I wish there were an easier way to do it. Even cosmic rays are very limited because even though there's lots and lots of them, they're very uncontrolled. We don't know the energies they're coming in with. There's not enough of them in a small area to do many experiments with. But we do have many particle physics experiments now that are more sort of big underground detectors that are sort of sitting and waiting for a lot of time and gathering data over time, rather than just having collider-based ones. Yeah.
Dr. Sheehy, we look forward to the mangoes and other fruits that you and accelerator physicists will discover in the future. Thank you so much for this talk.
Thank you very much.
I want to encourage everyone to check bookshopwestportal.com to purchase Dr. Sheehy's new book and to learn about the future of Bookshop West Portal events. Also, I got to say, please visit wonderfest.org to learn about future Wonderfest events and perhaps to contribute to Wonderfest's nonprofit mission of science outreach. I end this afternoon, or this morning for Dr. Sheehy, by offering three big thank yous. First, to Bookshop West Portal and Susan Tunis for bringing Dr. Sheehy to us. Second, to our Zoom audience, thank you for being here. And of course, to the author of The Matter of Everything, How Curiosity, Physics, and Improbable Experiments Changed the World, Dr. Suzie Sheehy. Good afternoon, good evening, and good morning, wherever you are. Hope to see you at a future event.